Tonight, we are going to use space the way people have always used the night sky. Not as something to solve quickly, and not as something to fear, but as something wide enough to make the noise of the day feel smaller. Space has a strange effect on the mind. The more you learn about it, the more impossible it seems, and yet the more calming it can become. A planet can have a day longer than its year. A moon can slowly leave its planet by the width of a few centimeters each year. A star can die and leave behind something so dense that a spoonful of it would weigh more than a mountain. There are worlds without suns, storms larger than Earth, and galaxies whose light began traveling before human beings existed. And still, all of this is real. This is not fantasy, and it is not a story made larger for drama. This is the universe we live inside, even on the quietest night, even when the room around you feels completely still. So for the next hour, you do not need to memorize anything. You do not need to follow one complicated argument. Let each strange space fact arrive naturally. Stay for a moment, and then drift into the next one. We can begin with one of the strangest ideas in modern cosmology. You have probably heard that nothing can move faster than light. That is true for objects moving through space. A spaceship cannot simply accelerate beyond light speed. A signal cannot break that limit. A planet, a star, or a particle cannot travel through space faster than light in the normal way. But the universe has a loophole. Space itself can expand. And when space expands, extremely distant galaxies can be carried away from us faster than light. They are not flying through space at that speed. The space between us and them is stretching. This is why there are parts of the universe we may never see. Their light may be trying to reach us, but the distance between here and there is growing too quickly. It is a little like walking toward a door while the hallway keeps getting longer. You may still be moving forward, but the door keeps slipping farther away. That means the observable universe is not the whole universe. It is only the part whose light has had enough time to reach us. Beyond that cosmic horizon, there may be galaxies, stars, planets, and entire histories that are real, but forever outside our view. They are not hidden behind a wall. They are simply being carried beyond reach by the quiet stretching of space. The next strange thought is much closer to home. The sunlight on your face is already old by the time it arrives. When you step outside on a bright day, the light feels immediate. It feels as if the sun is shining on you right now. But the sun is about 150 million kilometers away, and light needs a little over 8 minutes to cross that distance. So the sunlight you see now left the sun more than 8 minutes ago. If the sun somehow vanished in an instant, Earth would not know right away. For a little over 8 minutes, the sky would still look normal. Daylight would continue, and the planets would keep moving as if nothing had happened. Then the information would arrive. The light would stop, and the gravitational change would reach us too, because gravity's influence also travels at the speed of light. That delay is small enough to ignore in daily life, but enormous in meaning. When you look at the sun, you are looking slightly into the past. And this is true for everything in space. The moon is about 1¼ light seconds away. Jupiter can be tens of light minutes away. The nearest stars are years away. Some galaxies appear to us not as they are now, but as they were millions or billions of years ago. The night sky is not a live broadcast. It is an archive of old light, arriving patiently. Even the stars you see at night are not showing themselves in the present moment. Some of them may have changed since their light began traveling toward Earth. A star may look steady in your sky, while far away, it has already entered a different stage of life. This does not mean the night sky is fake. It means the night sky is layered with time. Every point of light has a travel story. Some light has crossed years. Some has crossed centuries. Some has crossed distances so large that human history happened while it was still on its way. When you look upward, you are not only looking across space, you are looking backward, into a sky full of delayed messages. Venus gives us another strange way to think about time. From a distance, Venus looks calm and bright. It is often called Earth's sister planet because it is similar in size and rocky like our world. But the deeper you look, the stranger it becomes. Venus rotates incredibly slowly. It takes about 243 Earth days for Venus to spin once on its axis, but Venus only needs about 225 Earth days to orbit the Sun. So on Venus, a day is longer than a year. A birthday could arrive before the planet finishes one full rotation. Even stranger, Venus rotates backward compared with most planets in the solar system. If you could somehow stand on its surface, the Sun would rise in the west and set in the east. Of course, standing there would not be easy. The surface is hot enough to melt lead, and the atmospheric pressure is crushing. Venus is a reminder that words like day, year, sunrise, and sunset are not universal rules. They are local habits. On Earth, they feel natural because we were born inside them. Elsewhere, time can move in ways that feel almost dreamlike. A year can pass before a day is done. A sunrise can come from the wrong side of the sky. A planet that looks gentle from far away can be one of the most hostile worlds near us. Venus has another strange detail hidden in its atmosphere. Its clouds are not soft water clouds like ours. They are made largely of sulfuric acid droplets. From space, those clouds make Venus bright and beautiful. They reflect sunlight so well that Venus becomes one of the brightest objects in our night sky. But that brightness is hiding a world of extreme heat, pressure, and chemical violence. This is one of the quiet tricks of astronomy. A planet can look peaceful from far away because distance removes the danger. Venus shines like a jewel, but up close, it is not gentle at all. Saturn has a different kind of strangeness. It is enormous. More than 700 Earths could fit inside Saturn by volume, and its rings stretch so far that the planet almost looks unreal. But Saturn's average density is lower than water. That means if you had an ocean large enough to hold it, Saturn would float. Of course, no normal ocean like that could exist. Saturn is not a solid ball you could gently place into water. It is a gas giant made mostly of hydrogen and helium, with violent weather, deep layers, and extreme pressures inside. Still, the comparison tells us something fascinating. Saturn is huge, but it is also spread out. Its size makes it feel heavy and solid in the imagination, but much of Saturn is made of light gases spread across a vast volume. Space often works like this. Something can be enormous without being dense, bright without being close, and empty without being simple. Saturn floats in the mind because the numbers say it could, and sometimes one number is enough to make a familiar planet feel strange again. Saturn's rings are also stranger than they look. From Earth, they seem like smooth, perfect bands. But the rings are actually made of countless pieces of ice and rock, ranging from tiny grains to chunks as large as buildings. They are incredibly wide, yet surprisingly thin compared with their diameter. In many images, the rings look solid, almost like a flat disk. In reality, they are more like a vast swarm of particles orbiting the planet together. Every piece is moving. Every fragment is following gravity. The whole structure looks calm because distance blends the motion into beauty. Saturn's rings are not a frozen decoration. They are an enormous moving system, delicate and violent at the same time. Jupiter is often described as Earth's protector. There is some truth to that. Jupiter's gravity is enormous, and over the history of the solar system, it has influenced the paths of countless comets and asteroids. Sometimes it pulls dangerous objects away from the inner planets. Sometimes it captures them. Sometimes it sends them into new paths. Without Jupiter, Earth's history may have been very different. But Jupiter is not simply a shield. Its gravity can also send objects inward. It can disturb comets and asteroids in ways that sometimes make the inner solar system more dangerous. not less. So Jupiter is not exactly a heroic guardian standing at the gate. It is more like a giant gravitational engine that shapes traffic, changes motion, and helps sculpt the architecture of the solar system. That is what makes it interesting. The solar system is not a perfectly calm model with planets moving peacefully forever. It is a gravitational environment where large objects keep influencing one another. Earth does not simply exist near Jupiter. Earth exists in a solar system partly shaped by Jupiter's weight. Jupiter also has a storm so large that Earth could fit inside it. The Great Red Spot has been observed for hundreds of years, though it has been shrinking over time. On Earth, even the strongest storms eventually lose strength. They run into land, cooler water, or changing atmospheric conditions. Jupiter has no solid surface like Earth's to break storms apart. Its atmosphere is deep, layered, and driven by powerful winds, so a storm can survive far longer than anything familiar to us. The Great Red Spot is not just weather. It is weather on a planetary scale, a storm watched by generations of humans, still turning in the clouds of a giant world. The Moon feels permanent, but it is slowly moving away from Earth. Each year, the Moon drifts about 3.8 centimeters farther from us. That is roughly the speed at which fingernails grow. The reason has to do with tides. The Moon's gravity pulls on Earth's oceans and creates tidal bulges. Because Earth rotates faster than the Moon orbits, those bulges are carried slightly ahead of the Moon. Their gravity gives the Moon a tiny pull forward, and over time, that tiny boost moves the Moon outward. At the same time, Earth's rotation is slowly slowing down, which means the days are very gradually getting longer. Nothing dramatic happens overnight. The change is tiny on human timescales, but across millions and billions of years, it matters. Long ago, the Moon was much closer. It would have looked larger in the sky. Earth's tides would have been stronger, and days would have been shorter. So when you look at the Moon, you are looking at a companion that is slowly leaving. Not in a sudden or violent way, but steadily, a little farther each year. On Earth, footprints vanish easily. Wind softens them. Rain erases them. Waves smooth them away. Plants grow over them. The ground changes because Earth is active, wet, and full of motion. The Moon is different. There is no breathable atmosphere, no rain, no flowing water, and no wind like we have here. So the footprints left by Apollo astronauts are still there. They may remain for millions of years, unless micrometeorites disturb them or future visitors walk over them. That fact is strangely moving. A human footprint is usually one of the most temporary marks imaginable. On Earth, a person walks across dust or sand, and soon the shape disappears. But on the Moon, a boot print can become almost geological. A small human trace can outlast civilizations. The same is true for rover tracks, landing marks, and equipment left behind. They rest in a quiet landscape under a black sky, preserved by the Moon's stillness. It makes the Moon feel less like a place we visited once, and more like a museum without walls, where silence helps memory survive. Mars has a volcano so large that it changes the meaning of the word mountain. Mount Everest is the tallest mountain above sea level on Earth. But Olympus Mons on Mars is much taller. It rises about 22 kilometers high, nearly 3 times the height of Everest above sea level. Its base is so wide that if you stood on the slope, you might not even realize you were standing on a volcano. The curve would be too gradual. It is not shaped like a sharp, dramatic peak. It is enormous, broad, and shield-like. Mars could grow a volcano this large, partly because its crust does not move the way Earth's tectonic plates do. On Earth, hot spots can create chains of volcanoes as plates move over them. But on Mars, the crust stayed more fixed over volcanic sources for long periods. Lava could build up in the same region again and again. The result is a mountain so large that it feels less like a mountain and more like a continent rising from the ground. Olympus Mons is a reminder that other planets do not obey Earth's limits. Mars also has a canyon that makes the Grand Canyon look small. It is called Valles Marineris, the giant canyon system on Mars, and it stretches for thousands of kilometers across the Martian surface. If you placed it on Earth, it would cross a huge portion of a continent. Its scale is difficult to picture because we are used to landscapes measured by human travel. A canyon on Mars can be so large that it becomes less like a place and more like a planetary scar. Mars is often imagined as empty and quiet, but its surface carries the memory of enormous geological events. The planet may be still now, but its ground tells a story of cracking, collapse, volcanism, and ancient change. Not every planet belongs to a star. Some planets drift through space alone. They are called rogue planets, and they may have formed around stars before being thrown away by gravitational interactions. Others may have formed more like small failed stars, collapsing from gas and dust without ever joining a normal solar system. A rogue planet has no sunrise, no familiar orbit around a warm parent star, and no daylight in the way we understand it. It moves through interstellar space in darkness. The idea sounds lonely, but rogue planets may be common. Some estimates suggest there could be billions of them in our galaxy. A planet without a star would be extremely cold on the surface, but that does not make it simple. If it had a thick atmosphere, internal heat, or a subsurface ocean, it might remain geologically interesting for a very long time. The strange part is not only that rogue planets exist, it is that the galaxy may be full of wandering worlds we cannot easily see, moving through the dark between the stars. Far beyond our solar system, there is a planet where glass may fall from the sky. Astronomers have studied a world called HD 1897-33b. From a distance, it appears blue, but it is not blue like Earth. Its color does not come from peaceful oceans. This planet is a hot gas giant, orbiting very close to its star. Its atmosphere is extremely hot and violent. Scientists think tiny particles of silicate may exist in its atmosphere. Silicate is the kind of material found in glass. Winds on this planet may reach thousands of kilometers per hour. So the image is almost unbelievable. A blue planet where glass-like particles may whip through the atmosphere sideways at terrifying speed. It is beautiful from far away, but deadly up close. This is one of the strange things about exoplanets. They remind us that color can lie. A blue world does not always mean water, and a bright atmosphere does not always mean safety. Sometimes beauty in space is just violence seen from a distance. Now we can drift farther away from the familiar planets and into stranger objects. Some of the most extreme things in the universe are not always the largest. Sometimes they are small, dense, fast, and almost impossible to imagine with ordinary human instincts. There are stars so dense that a teaspoon of their material would weigh about as much as a mountain. These stars are called neutron stars. They are the collapsed cores of massive stars that exploded as supernovae. After the explosion, the remaining core is crushed by gravity into an object only about the size of a city, but with more mass than the Sun. That means the matter inside is packed to an almost unimaginable degree. Atoms are crushed. Electrons and protons are forced together. The star becomes a dense sphere made mostly of neutrons. A neutron star is not large in the way we expect stars to be large. It is large in mass, but small in size. Something with the mass of a star can be compressed into a sphere only around 20 kilometers wide. If you could stand on the surface, which you could not, gravity would be unbelievably strong. Neutron stars show us that in space, small does not always mean gentle. Sometimes the smallest looking object is one of the most extreme things in the universe. Some neutron stars spin incredibly fast. These are called pulsars. A pulsar can rotate many times per second, sometimes hundreds of times per second. As it spins, beams of radiation sweep through space. If one of those beams points toward Earth, we see regular pulses, almost like the ticking of a cosmic clock. The first pulsars were so precise and strange that scientists briefly wondered whether they could be signals from an intelligent civilization. They were not. They were natural objects, but no less astonishing. A pulsar is a dead star crushed into a city-sized sphere, spinning at impossible speed, sending beams through the darkness with extraordinary precision. The universe is often chaotic, but pulsars show that nature can also create rhythms so regular they almost feel designed, even though no machine is turning them and no lighthouse keeper is inside. It is only gravity, rotation, magnetism, and the remains of a dead star. Some neutron stars become even stranger than pulsars. They become magnetars. A magnetar has an extremely powerful magnetic field, far stronger than anything we experience on Earth. The magnetic field can be so intense that it affects the behavior of matter around the star in extreme ways. Magnetars can release sudden bursts of high-energy radiation, making them some of the most dramatic dead stars known. The strange part is that a star can die and still remain violently active. Death in space does not always mean silence. Sometimes it means the star has become smaller, denser, faster, and far more dangerous than before. A magnetar is not bright and comforting like the sun. It is a collapsed remnant with a magnetic field so powerful that ordinary language almost fails around it. Stars are born inside clouds. These clouds are called nebulae, and some of them are enormous. They can stretch for many light years, filled with gas, dust, and regions where gravity slowly gathers material together. Inside these clouds, dense pockets can collapse. As the material falls inward, it heats up. Eventually, if enough mass collects, nuclear fusion begins. A star is born. It is strange to think of stars as things that have nurseries, but they do. They begin in cold, dark, dusty regions of space. They are not born shining. They become light after gravity has done enough work. Our own sun formed this way, from a cloud of gas and dust more than 4.5 billion years ago. That means the light-warming Earth began as darkness. Before there was daylight on Earth, there was dust, gravity, and collapse. Before our oceans existed, something in space had to gather itself together and ignite. The atoms in your body were made in stars. This is one of the most famous space facts, but it is still one of the strangest. Hydrogen and helium formed very early in the universe, but heavier elements like carbon, oxygen, calcium, and iron were created inside stars or during stellar explosions. The carbon in your cells, the oxygen you breathe, the iron in your blood, and the calcium in your bones all have cosmic histories. They were not made on Earth first. They were forged in earlier generations of stars, scattered into space, and later became part of new stars, planets, oceans, rocks, and living bodies. This does not mean you are special in a sentimental way. It means you are chemically connected to the history of the universe. Your body is not separate from space. It is one of the forms space eventually learned to take, a quiet continuation of ancient stars breathing on a small planet. Some planets may contain enormous amounts of carbon. Under extreme pressure, carbon can form diamond. This has led scientists to consider whether certain carbon-rich planets could contain diamond-like material deep inside them. One famous candidate often discussed is 55 Cancri e, a super-Earth orbiting a nearby star. The early idea of a diamond planet may be more complicated than it first sounded, but the possibility remains fascinating. Planetary chemistry can vary dramatically. Not every rocky planet is built like Earth. Some worlds may have interiors and mineral structures that would feel completely unfamiliar to us. The important idea is not that there is a perfect, sparkling diamond planet nearby. The stranger idea is that planets can be made with recipes we do not experience here. Earth is not the template for all worlds. It is only one version of what a planet can become. Far out in the solar system, the sun begins to look very different. From Pluto, sunlight is much weaker than it is on Earth. The sun would still be the brightest object in the sky, but it would no longer dominate the sky in the way we know. Noon on Pluto would be dim, cold, and distant. The same sun that makes deserts burn on Earth becomes a small, intense point in Pluto's sky. Distance changes everything. The sun is not less powerful. Pluto is simply far enough away to make daylight feel almost like memory. Comets are sometimes described as dirty snowballs, but that phrase makes them sound too simple. A comet is a frozen remnant from the early solar system. It contains ice, dust, rock, and ancient material that has been preserved for billions of years. When a comet comes close to the sun, it warms up. Ice turns directly into gas, and dust escapes from the surface. This creates a glowing coma, and sometimes a long tail stretching away from the sun. That tail can be millions of kilometers long, but it is extremely thin. If you could somehow pass through a comet's tail, it would not feel like flying through smoke or fog. The material is spread across such a huge volume that it would be far emptier than anything we experience on Earth. A comet can look dramatic in the sky while being incredibly delicate. That is one of space's quiet tricks. Something can appear huge and bright, but still be almost nothing when measured by density. A comet's tail is not a solid banner. It is a trace of ancient ice, briefly glowing as it is pulled into sunlight. There are places in space colder than almost anywhere else in the universe. One of the coldest known natural places is the Boomerang Nebula. It is a cloud of gas surrounding a dying star, and parts of it are colder than the cosmic microwave background, the faint afterglow left from the early universe. That is strange because the background radiation fills space. It gives the universe a very low baseline temperature. But the Boomerang Nebula is even colder in some regions because gas has been expanding rapidly away from the central star. As it expands, it cools. The result is a place that is colder than the surrounding universe. This feels backward at first. We often imagine space as simply cold, but even coldness has degrees. A dying star can create one of the coldest known environments in nature, colder than the ancient glow left behind by the early universe. Black holes are often imagined as cosmic vacuum cleaners. That image is misleading. A black hole does not automatically suck in everything around it. If the sun were somehow replaced by a black hole with the same mass, Earth would not suddenly fall in. It would continue orbiting, because the gravitational pull at Earth's distance would be the same. What makes a black hole special is not that it reaches across the universe and pulls everything in. It is that, once you get too close, there is a boundary you cannot cross back from. That boundary is called the event horizon. Outside it, escape may still be possible. Inside it, every future path leads deeper inward, even for light. This is what makes black holes so strange. They are not just objects in space. They are regions where space and time themselves behave in extreme ways. The danger is not magical suction. The danger is crossing a line where the universe stops giving you exits. Near a black hole, time itself changes. To someone far away, an object falling toward a black hole would appear to slow down as it approached the event horizon. Its light would stretch, becoming redder and dimmer. From the falling object's own point of view, time would feel normal locally, at least until conditions became fatal. This difference comes from relativity. Gravity affects time. The stronger the gravity, the more time slows relative to regions with weaker gravity. This is not just a strange idea for black holes. It also happens, very slightly, near Earth. Clocks at different altitudes tick at slightly different rates because gravity is not exactly the same everywhere. Near a black hole, the effect becomes extreme. That means time is not one universal river flowing the same way everywhere. Time depends on where you are, how you move, and how strong gravity is around you. The universe does not have one single clock. Every place carries its own version of time. Near a black hole, light can take strange paths. There is a region where gravity is so strong that light can move around the black hole in an orbit-like path. This region is often connected with what scientists call the photon sphere. The idea feels impossible because we are used to light moving in straight lines. But light follows the shape of space-time. Near a black hole, space-time is curved so deeply that straight paths no longer look straight to us. A black hole does not simply pull matter. It reshapes the possible paths that anything can take. Even light, the fastest thing in the universe, must follow the geometry around it. This is why black holes are not just dark objects. They are places where the map itself has changed. Some planets complete a year in only a few hours. These are ultra-short period planets, worlds orbiting extremely close to their stars. They can complete an orbit in less than one Earth day. Imagine a planet where a year passes while you sleep. A world like that is not gentle. It is usually scorched by intense radiation. Its surface may be molten or stripped by its star's energy. But the orbital speed is the strange part. On Earth, a year feels like a large unit of life. Seasons change, birthdays return, and the planet completes its long path around the sun. On some worlds, that entire cycle is compressed into hours. The word year becomes almost unrecognizable. It no longer means winter, spring, summer, and autumn. It means one tight loop around a nearby star, a complete orbit between one evening and the next morning. Some moons may hide oceans beneath ice. Europa, one of Jupiter's moons, is one of the most famous examples. From the outside, it looks frozen. Its surface is covered in ice, marked by cracks and ridges. But beneath that ice, scientists think there may be a global ocean of liquid water. The ocean could exist because of tidal heating. Jupiter's gravity pulls on Europa, and interactions with other moons stretch and squeeze it slightly as it orbits. That flexing can generate internal heat. So even far from the sun, a moon can remain warm inside. This changes the way we think about habitability. A world does not need to sit on a sunny beach in space to be interesting. It might hide its ocean under ice. It might be dark on the surface, but active below. Europa reminds us that some of the most important places in the search for life may not look inviting at first. They may look frozen, silent, and closed. Another moon, Enceladus, sends material from its hidden ocean into space. Enceladus orbits Saturn, and it is covered in bright ice. Near its south pole, geysers shoot water vapor and icy particles outward through cracks in the surface. This is extraordinary because it gives scientists a way to sample material from inside the moon without drilling through the ice. Spacecraft have flown through these plumes and detected water, salts, and organic molecules. That does not prove life exists there, but it does mean Enceladus has some of the ingredients that make scientists pay attention. A small icy moon, far from the warmth of the sun, may contain a hidden ocean with chemical activity. From far away, Enceladus looks quiet. But it is not simply frozen. It is leaking clues, and it makes the solar system feel less empty than it first appears. Titan, Saturn's largest moon, has weather, rivers, lakes, and seas. But they are not made of water. Titan is extremely cold, so methane and ethane can exist as liquids on its surface. These hydrocarbons form clouds, rain, rivers, and lakes. In a strange way, Titan is one of the most Earth-like worlds we know, not because it is comfortable, but because it has a thick atmosphere and an active surface cycle, with liquids moving between sky and ground. On Earth, water shapes landscapes. On Titan, methane and ethane do some of that work. This means Titan has familiar patterns made from unfamiliar materials. Rain falls there, rivers carve the surface, and lakes collect under Titan's cold orange haze. Titan shows us that Earth-like does not always mean Earth-like in chemistry. Sometimes it means the same kind of process, rewritten with different ingredients. Uranus rotates on its side. Most planets spin with their poles roughly upright compared with their orbit, though each one has its own tilt. Uranus is different. It is tilted by about 98 degrees, which means it rolls around the Sun almost on its side. This gives Uranus extreme seasons. For part of its long orbit, one pole can face the Sun for years, while the other remains in darkness. Then, over time, the situation changes. A season on Uranus is not a few months. It can last more than 20 Earth years. Scientists think Uranus may have been knocked sideways by a massive collision long ago, though the exact details are still studied. The result is a planet that does not simply spin. It tumbles through its orbit in a way that feels visually wrong. Uranus is a reminder that the solar system has a violent past. The planets may look calm now, but many of their present shapes and motions were created by ancient impacts, migrations, and gravitational accidents. Neptune has some of the fastest winds in the solar system. Even though it is far from the Sun and receives much less solar energy than Earth, its atmosphere is extremely active. Winds on Neptune can reach speeds far beyond the strongest hurricanes on Earth. This seems surprising because we often connect weather with sunlight. The Sun heats Earth's atmosphere and helps drive winds, storms, and climate systems. But Neptune has internal heat. It radiates more energy than it receives from the Sun, and that energy helps drive atmospheric motion. The result is a cold, distant planet with powerful winds and enormous storms. Neptune proves that distance from the Sun does not always mean stillness. A world can be dark and cold, yet intensely active, sitting near the edge of the solar system, with an atmosphere still in motion. Even small worlds can have companions. We often imagine moons as companions of planets, but asteroids can have moons too. Some asteroids are orbited by smaller objects, and some form binary systems where two bodies orbit around a shared center of mass. This happens because gravity does not only belong to planets. Anything with mass has gravity, even if the pull is tiny. In the asteroid belt and beyond, collisions, close encounters, and rotational effects can create small systems with more than one body. This makes the solar system feel more intricate. It is not just planets and moons in a simple hierarchy. There are small worlds with companions, rubble piles holding together by weak gravity, and fragments from ancient collisions moving in quiet pairs. Even the leftover pieces of planetary formation can have their own small relationships. Some stars move so fast that they may escape the galaxy. They are called hypervelocity stars. Some may have been flung outward after close interactions with the supermassive black hole at the center of the Milky Way. Others may come from violent stellar encounters or supernova explosions in binary systems. A star is not something we usually imagine being thrown. It feels too large, too powerful, too permanent. But gravity can do astonishing things. Under the right conditions, a star can be accelerated to extreme speed and sent racing through the galaxy. Some of these stars may eventually leave the Milky Way entirely. It is difficult to picture a whole sun becoming a traveler, leaving the galaxy that formed it and moving into intergalactic space. Now the journey becomes wider. We have moved through planets, moons, storms, dead stars, black holes, and wandering worlds. But the universe is not strange only because of the objects inside it. It is also strange because of the invisible things shaping it, the old light still crossing it, and the enormous future waiting far beyond anything human beings will ever see. Dark matter is one of the greatest mysteries in modern science. We cannot see it directly because it does not emit, absorb, or reflect light in the normal way. But galaxies behave as if there is more mass present than we can observe. Stars orbit too quickly around galactic centers. Clusters of galaxies bend light in ways that suggest extra invisible mass. The large-scale structure of the universe also points toward something unseen, helping shape cosmic evolution. Scientists call this unseen mass dark matter. It is not dark because it is black like coal. It is dark because it does not interact with light in the way ordinary matter does. We know it seems to be there because of gravity, but we do not yet know what it is. That is the strange part. Most of the matter in the universe may be something we have never directly touched, seen, or fully understood. Dark energy is even stranger. If dark matter helps hold cosmic structures together through gravity, dark energy seems connected to the accelerated expansion of the universe. In the late 20th century, scientists discovered that the expansion of the universe is not simply slowing down under gravity, it is speeding up. The name dark energy is really a placeholder for our ignorance. It describes whatever is causing this accelerated expansion, but it does not mean we fully understand its nature. This is one of the deepest mysteries in cosmology. The universe is not just expanding, its expansion is accelerating. Distant galaxies are being carried away faster over time. The future of the universe may depend on something invisible, spread throughout space, pushing cosmic history toward a colder, more distant future. Dark energy is not strange because it is dramatic. It is strange because it may quietly control the fate of everything. There may be more stars in the observable universe than grains of sand on Earth's beaches. This comparison is often used because it gives the mind something familiar to hold. A handful of sand already contains thousands of grains. A beach contains more than anyone would want to count. All the beaches on Earth feel like an impossible number, and yet, the observable universe may contain more stars than that. The number is not only large, it is emotionally large. It makes Earth feel small, but not in a meaningless way. More like standing at the edge of something too vast to finish imagining. Every star may have its own history. Many may have planets. Some planets may have moons, and some moons may hide oceans. The sky is not sprinkled with lights, it is filled with places. Every point of light is a reminder that our local experience is only one tiny part of a much larger cosmic landscape. The Milky Way is on a collision course with Andromeda, but there is no need to worry tonight. The collision will not happen for billions of years, and when galaxies collide, the stars inside them usually do not crash into each other. The distances between stars are so enormous that they mostly pass through the spaces between one another. But the galaxies themselves will be transformed. Their shapes will stretch, twist, and merge. Gas clouds may collide and trigger new star formation. Over a long time, the Milky Way and Andromeda may become one larger galaxy. The strange part is that something as enormous as a galaxy can have a future encounter already written into its motion. The night sky looks still because human lives are short. But on cosmic timescales, galaxies move. They approach, interact, and reshape one another. The Milky Way is not frozen in space. It is traveling through a universe where even galaxies have destinations. The center of the Milky Way contains a supermassive black hole. It is called Sagittarius A star. It has millions of times the mass of the Sun, packed into a region far smaller than the galaxy around it. We cannot see the black hole itself, but we can observe its influence. Stars near the center of the Milky Way orbit around an invisible, massive object, moving in ways that reveal what must be there. This is one of the most beautiful methods in astronomy. You do not always see the thing directly. Sometimes you watch what moves around it. You study the dance, and from the dance, you infer the dancer. Sagittarius A star is quiet compared with some supermassive black holes in other galaxies, but it is still extraordinary. At the center of our galaxy, hidden behind dust and distance, there is a dark gravitational heart, and the stars around it are tracing its presence. The universe has a leftover glow from its beginning. It is called the cosmic microwave background. This radiation comes from a time when the universe became cool enough for light to travel freely. Before that, the early universe was hot, dense, and opaque. Light could not move through it easily. Then, as the universe expanded and cooled, atoms formed and light was released. That ancient light has been traveling ever since. Today, it has stretched into microwave radiation, filling the universe in every direction. When scientists study it, they are not seeing the Big Bang itself, but they are seeing a very early afterglow, almost like a baby picture of the universe. The strange thing is that no matter where you look, this faint signal is there. The sky is not truly empty. It carries the cooled remains of the early universe. Every direction contains a whisper from a time before stars, before planets, and before galaxies as we know them. Some galaxies are so far away that we see them as they were near the beginning of cosmic history. Because light takes time to travel, looking far into space also means looking far into the past. A very distant galaxy is not shown to us as it is today. Its light may have traveled for billions of years before reaching our telescopes. This means astronomy is also time travel, but only in one direction. We cannot visit the past. We receive it. Ancient light arrives at Earth carrying information about worlds and galaxies that may have changed completely by now. Some stars in distant galaxies may no longer exist. Some galaxies may have merged. Some regions may have transformed beyond recognition. But their old light is still arriving. The universe lets us look backward because light is not instant. The farther we see, the older the message becomes. Some stars die quietly. Others die violently. When a massive star reaches the end of its life, it can explode as a supernova. For a brief time, the explosion can shine with the brightness of an entire galaxy. The star throws its outer layers into space, scattering heavy elements that can later become part of new stars and planets. Supernovae are destructive, but they are also creative. Without them, many of the elements needed for rocky planets and life would not be spread through space in the same way. This is one of the universe's strange patterns. Creation often follows destruction. A star dies, and its material becomes available for new worlds. The iron in a planet, the calcium in bones, and the oxygen in an atmosphere may all trace back to older generations of stars. A supernova is not just an ending, it is a redistribution. The universe breaks something open, and the pieces become future possibilities. White dwarfs are stellar remains that can stay warm for an unbelievably long time. When a star like the Sun reaches the end of its life, it does not explode as a supernova. It sheds its outer layers and leaves behind a dense core called a white dwarf. A white dwarf no longer performs fusion in the way a normal star does. It slowly cools over time. But space is old, and white dwarfs cool very slowly. In theory, after an almost unimaginable amount of time, a white dwarf could cool into a black dwarf. But the universe is not old enough for black dwarfs to exist yet. That is the strange part. There are objects that physics predicts, but time has not had enough time to make them. The universe is ancient, but not ancient enough for everything possible to have happened. Some cosmic objects may belong only to the far future. They are not impossible. They are waiting for time. Some stars fail before they truly become stars. They are called brown dwarfs. A brown dwarf forms from gas and dust, like a star, but it does not have enough mass to sustain stable hydrogen fusion in its core. It is bigger than a planet, but not quite a true star. This makes brown dwarfs strange in-between objects. They can glow faintly from heat left over from their formation, but they do not shine like ordinary stars. They are sometimes called failed stars, although that phrase is a little unfair. They are not mistakes. They are their own kind of object. Brown dwarfs remind us that nature does not always fit into clean categories. Words like planet, star, moon, and asteroid help us organize the universe, but nature does not always respect those borders. Some objects live between definitions, and those are often the most interesting ones. The solar system has a boundary, but it is not a wall. Far beyond Neptune lies the Kuiper Belt, a region filled with icy bodies, dwarf planets, and remnants from the early solar system. Farther still, there may be the Oort cloud, a vast, distant shell of icy objects surrounding the Sun. The Oort cloud has never been directly observed in the same simple way we see planets, but it is thought to be the source of many long-period comets. If it exists as expected, it stretches incredibly far from the Sun. The strange thing is that the solar system does not simply end after the last planet. It fades. The Sun's family becomes thinner, colder, and more distant. There is no signpost saying the solar system is over. There are just fewer objects, weaker sunlight, and larger distances. Space rarely ends sharply. It dissolves into more space. There are places between galaxies that are almost unimaginably empty. Inside galaxies, there are stars, gas, dust, planets, and dark matter. But between galaxies, ordinary matter becomes extremely thin. A person drifting there would see darkness in nearly every direction, with galaxies appearing as distant islands of light. Intergalactic space is not completely empty, but compared with the environments we know, it is profoundly sparse. This kind of emptiness is hard to imagine because human life happens in dense surroundings. Air presses around us, ground supports us, objects fill rooms, cities glow with movement. But between galaxies, the universe becomes quiet on a scale that almost removes meaning from the word quiet. There may be particles, faint radiation, and invisible dark matter, but there is almost nothing familiar. It is space between the islands, a cosmic ocean with galaxies scattered through it like distant lights. Some regions of the universe are emptier than others. They are called cosmic voids. A cosmic void is a vast region with far fewer galaxies than average. These voids can stretch across enormous distances, forming part of the large-scale structure of the universe. Galaxies are not spread evenly everywhere. They form filaments, clusters, and walls, with great empty regions between them. From far enough away, the universe begins to look almost like a web. Matter gathers along strands, galaxies collect in bright knots, and between those structures, the voids open like dark spaces in the pattern. The strange part is that emptiness itself has structure. The universe is not simply full of things, it is shaped by where things are missing. Some signals from space arrive as brief bursts, and we still do not fully understand all of them. Fast radio bursts are intense flashes of radio energy that last only milliseconds. Some come from distant galaxies, some repeat. Others have been detected only once. Scientists have made progress in connecting some of them to extreme objects like magnetars, but the full picture is still being studied. The strange thing is the combination of power and brevity. A signal can cross enormous cosmic distances, arrive at Earth, and be over almost instantly. For a human listener, it would be nothing. For a radio telescope, it can be a clue from deep space. The universe does not always speak in long messages. Sometimes it sends a flash. Some stars are so large that if placed where our Sun is, they would swallow the inner planets. These are red supergiants. They are stars near the end of their lives, swollen to enormous sizes after using up fuel in their cores. Their outer layers expand outward, becoming cool and diffuse compared with hotter stars, but their size becomes difficult to imagine. A red supergiant can be hundreds of times wider than the Sun. If one replaced the Sun, its surface could extend beyond the orbit of Mars, depending on the star. These stars are not stable forever. Many will eventually explode as supernovae, scattering material into space. A red supergiant is strange because it feels both huge and fragile. Its outer layers are spread far into space, while its core moves toward a violent ending. A star can become enormous just before it dies. The universe may end in a long, cold fading. One possible future is called heat death. In this scenario, stars eventually burn out. New star formation slows and stops. Galaxies grow darker. Black holes slowly evaporate over enormous timescales through a process related to Hawking radiation. The universe does not end with a dramatic explosion. It simply runs out of usable energy. Everything spreads out, cools, and becomes more uniform. This is not an event anyone would watch. It is a future so distant that the numbers become difficult to feel. But the idea is strangely powerful. The universe may not end with fire. It may end with a gradual silence, stretched over timescales far beyond human imagination. The final strange thought for tonight is also the simplest. We are inside space. It is easy to talk about space as if it is somewhere else, a place above us, a dark background, or a distant stage where planets and stars perform. But Earth is not outside the universe looking in. Earth is in space. We are moving around the sun. The sun is moving around the Milky Way. The Milky Way is moving through the local group. Everything is in motion, even when life feels still. Right now, as you listen, you are not sitting in a fixed place. You are being carried by a rotating planet, around a star, through a galaxy, inside an expanding universe. Nothing about that feels dramatic in daily life. The room may be quiet, and the night may feel still. But beneath that stillness, you are traveling, and you always have been. Maybe that is the calmest, strange fact of all. Space is not only above you, it is where you are. So let the thought become soft now. The universe is vast, old, dark, and full of things that do not behave the way our instincts expect. But tonight, you do not need to solve it. You only need to rest inside it. The stars can keep burning, the galaxies can keep drifting, and the moon can keep moving away by a few quiet centimeters each year. You can let the scale of it all become gentle, not something to fear, and not something to finish understanding. Just a wide, dark sky, slowly opening while you fall asleep.